Welcome back to the Deep Dive. Today we are focusing on one of those subjects that sits right at the intersection of civil rights, construction engineering, and surprisingly brilliant physical design.
It really is a fascinating mix.
It is. We are taking a deep dive into the ADA CAT Toolkit, which is this specialized system built to take the often complex, ratio-filled, high-stakes requirements of the Americans with Disabilities Act
Right.
and make them instantly verifiable.
That's the core mandate, the ADA CAT system,
Yeah.
or the Accessibility Compliance Assessment Tool. Its entire purpose is fundamentally trying to democratize auditing.
Democratize it. How? Exactly.
Well, the goal is to move the whole conversation about accessibility away from anecdote, away from did this one person manage to squeeze through the doorway, and into a standards-based, quick pass-fail analysis. And it does that by combining this physical toolkit we're going to discuss with a really powerful, comprehensive online component for audits and reporting.
And what immediately jumps out at you is that this isn't just a collection of standard contractor tools.
Yeah, not at all.
I mean, yes, there's a tape measure and a spirit level, but the true genius lies in these custom-engineered devices. They were literally built to eliminate the need for complex trigonometry or calculating fractions on site.
Exactly.
We're going to unpack the design secrets hidden inside things like the magic slope block and the mighty sparkling story stick.
But before we even get to the gadgets, I think we have to ground this in the philosophy of compliance itself, because it's often, misunderstood.
Okay.
The ABA guidelines are not a target to aim for. They define the absolute minimum requirements for accessibility.
So it's the floor, not the ceiling.
It's the floor. And legally, for a facility to be truly acceptable, it should be striving for 100% compliance. If you have any barriers remaining, you are fundamentally failing the standard.
And that immediately hits you with the paradox of partial accessibility. The sources make a really powerful point about this.
They do?
If a building's interior is architecturally flawless, all the bathrooms are compliant, all the shelves are reachable, but the entryway ramp has a slope that's just a little too steep for a wheelchair user.
All that interior work is useless.
Right. All that interior compliance is wasted effort for that specific customer. It's like a 99% score that results in 0% access.
It creates a totally unnecessary bottleneck. And this leads right into ADA CAT's novel solution, something they call targeted audits.
So what does that mean? Instead of just a generic checklist?
Yeah, instead of looking at every barrier equally, the system forces assessors to match the requirement to the specific functional limitation group that benefits.
Can you walk us through a practical example of that?
Sure.
My instinct would be to just, fix the biggest, most obvious problem first, regardless of who it helps.
Right, but the system refines that. So if you're checking for curb cuts and ramp slopes, you are auditing for mobility users. If you are checking for, say, correct signage contrast and font dimensions.
That's for visually impaired users.
Exactly. And if a business finds they have dozens of barriers, they often have limited resources for fixing them. So instead of spreading a small budget across all these areas, which results in partial, incomplete fixes that don't really satisfy any group.
They can make a strategic decision.
Precisely. They stop thinking horizontally across all the problems and start thinking vertically, focusing on one specific population.
So they might say, this year our goal is 100% access for wheelchair users.
Exactly that. They might commit their entire budget in year one to achieving that full access addressing ramps, door widths, restroom stalls, and just ignore signage contrast for the year.
And then the next year they shift focus.
The next year they might shift focus to sensory issues, ensuring full access for deaf customers, and so on. This guarantees that by the end of year one group has full access, rather than all groups having only partial access.
Wow.
The online system actually categorizes this into 14 different functional limitations to guide that targeting.
That is a fundamental, almost ethical shift in how you allocate resources. It changes how you measure success entirely. Okay, let's transition from the philosophy to the mechanisms that remove the math.
The fun stuff.
The fun stuff. Slope is defined by those tricky ratios, like 1.1 or 1.48. How does the magic slope block eliminate that calculation?
Well, slopes are tricky because they rely on rise over run. It's a fraction, right? A 1.12 slope means for every 12 inches you go horizontally, you can only rise 1 inch vertically.
And normally you'd need a calculator for that.
Or charts, yeah. You'd need something to do the math. The tool, though, it utilizes a standard 24-inch spirit level. That 24-inch length is the crucial constant. That's your run.
Right.
The magic slope block then provides the corresponding vertical rise, for the maximum allowed slope over that 24-inch distance.
And the block itself has all the different required slopes.
All 4 key ADA maximums are encoded on its different edges, from the very gentle 1.48 all the way up to the maximum permitted 1.12.
So you just select the 1.12 edge on the block, place the level on the ramp surface, and you put the block underneath the downhill end.
You've got it. The block is pre-calculating the required rise over run for that 2-foot span.
And what do you look for in the bubble?
It's simple. If the bubble in the level remains centered, or if it's displaced toward the block, your slope is acceptable. It's actually flatter than the maximum allowed.
But the fail condition is just as clear.
Crystal clear. If the bubble is displaced away from the block, even slightly, say, a quarter of the bubble is outside the lines, it means the ramp is steeper than 1.4. And it fails. Instantly.
That is truly elegant, pure geometry. Okay, now let's move to the story stick, which is engineered to identify barriers that, as able-bodied individuals, we don't register them.
We step right over them. Yeah, these are the vertical offsets, and this is where the physical experience of moving through an environment gets translated into a mechanical test.
And it all comes down to the wheel.
The wheel is paramount. It's a 3-inch polyurethane wheel, and it was deliberately chosen because it mimics the front casters on ultralight wheelchairs. It represents a critical worst-case scenario for wheeled mobility aids.
And as you roll it, what are you listening for? Is there a feedback mechanism?
You are listening for a very distinct sound. The maximum allowed vertical change, that tiny little lip in the sidewalk or the transition between 2 types of flooring, is 1/4 of an inch.
Okay.
When the wheel hits exactly 1/4 of an inch, it produces a clear, audible thump. Anything above that is a major barrier. At a 1.5-inch bump, the stick just stops cold.
A literal physical interruption.
It is. I love the detail from the manual, too, about the wheel.
But it sparkles when it rolls. I saw that. It seems like such a fun, non-technical detail.
It absolutely serves a function, though. It's a public awareness function. When an assessor is working, people notice the flashing lights and they ask, "What are you doing?"
It's an icebreaker.
It's an easy icebreaker to explain that the surface they walk over every single day without thinking about is actually a major obstacle for other people. It turns the assessment into a teaching moment.
The story stick isn't just a bump detector, though. It's also a high-precision vertical ruler. It has these key ADA heights encoded directly onto the shaft.
Yeah, when you hold it vertically, you can quickly check control heights. The 15-inch mark is the lowest acceptable reach for controls or shelves.
But there's a caution there, right? You have to measure to the point of use.
A critical caution. The source mentions a vending machine where the coin slot is 40 inches high, which is fine, but the dispensing bin floor where your item actually lands is only 6 inches off the ground.
So the reach to get your soda is way too low.
It's too low and it fails compliance. Even though the machine's front face looks totally acceptable, you have to measure where the action happens.
That makes perfect sense. What about accessible seating?
Accessible seating height falls between 17 and 19 inches, and this is one place where you have to account for compression. A soft cushion might look too high when it's empty.
But once someone sits on it.
The weight of a person may compress it down into that compliant range, so you have to test that.
And moving on up the stick.
We hit 27 inches. That's the required knee space clearance beneath sinks or desks. Again, you have to watch out for recessed frames or structural supports that might reduce that clearance.
Right.
Then you get into the hand support ranges. Grab bar height in stalls or showers is 33 to 36 inches. And handrail height along stairs or ramps is slightly higher at 34 to 38 inches.
And there's a specific way to measure that on stairs, isn't there?
There is. Crucially, when measuring a stair handrail, you must always measure from the nosing, which is the leading edge of the stair tread.
And the full 60 inches of the extended stick.
That serves 2 major functions. It measures the required 5-foot or 60-inch clear diameter for a wheelchair turning space.
The turning circle.
Exactly. And it also serves as the maximum acceptable baseline height for overhead signage.
Before we leave the story stick, it performs a crucial field test for surface integrity firm, stable, and slip resistant. And this test requires no chemistry, just physics.
Just physics. You turn the wheel 90 degrees to the handle, and you push down hard enough to put a slight bow in the stick.
And you're looking for 3 different kinds of failure.
3 things. If the surface shifts, imagine loose paving stones, it's unstable. If the wheel digs in, like through loose gravel or deep carpet, it's not firm. And if the wheel slips across the surface, especially polished flooring, it's not slip resistant.
And you have to test it wet and dry.
You must test both. Many floors that pass when they're dry fail miserably when they get wet.
Incredible detail. We also have 2 specialized force measurement tools in the kit. And I'm fascinated by the key torque tool, which measures an accessibility barrier that is actually not covered by the ADA.
That's a critical point. The ADA sets standards for physical structure, but not necessarily for the force required for fine motor tasks, like turning a key.
But for someone with limited grip strength or arthritis, a stiff lock is an absolute barrier.
It's a complete barrier. So the key torque tool is designed to address this gap. It measures the force required to turn a key in a lock, standardized at 1 foot-ounce of torque.
And the pass-fail test literally uses gravity.
It does. You place the cross slot horizontally over the key. If the lock passes, meaning it requires 1 foot-ounce of torque or less, gravity will just rotate the tool downward as soon as you release it.
And if it stays put.
If the lock is too stiff, the tool remains horizontal or barely moves. That's a fail. It's an immediate, crucial indicator of real-world usability beyond the structural code.
And the final force tool, the door force tool. This measures the force required to open a door. Doors shouldn't exceed 5 pounds of pressure, right?
That's the standard. But the common mistake here, especially in modern, well-sealed buildings, is ignoring air pressure. You get highly inaccurate readings if you try to pull a sealed door open because you're measuring the resistance of the lock mechanism plus the air pressure difference.
So what's the correct technique?
The critical step is to break the air seal. First, use your toe or a small block to hold the door just slightly ajar, and then apply the tool to get a true measure of the required force.
And the little O-ring on the tool.
The O-ring slides up to mark the maximum force applied. It gives you a really easy visual result.
Okay, we've covered physical movement and force. Now let's tackle what sounds like the most mathematically terrifying part of compliance. Tactile signage and how the font guide performs miracles using geometry.
This is where engineers often pull their hair out. Signage compliance requires the letter height to be between 58 and 2 inches. That part's easy.
Right.
But then all other elements, the width of the font, the spacing between letters, the distance between lines, they all have to be complex proportions of that initial height.
Like the stroke width.
For example, the stroke width must be exactly 15% of the font height. So if you have a 1-inch letter, you have to calculate 15% of an inch for the stroke width on the fly, and there is no acceptable range.
So if the height of the letter changes, all the ratios change, and you need a calculator and a chart for every single sign you look at.
You do, which is why this tool is so brilliant. The font guide, these 2 clear plastic pieces joined by a pivot, it manages to program all those calculations instantly.
How does it do that? How does it translate height into all those other proportions?
The pivot and the reference lines translate the height into an angle that then fixes all the required proportions. First, you align the pivot at the baseline of the letter you're measuring.
Okay.
Then you rotate the protractor until the protractor reference line crosses the arm reference line precisely at the very top of the letter. At that moment, you have programmed the guide with the proportional math specific to that font height.
So the angle now represents 100% of the letter height. And now you can test all the adjacent elements.
Correct. Let's start with line spacing. If there's a line of text above, its baseline has to cross the reference line within the dedicated line spacing window.
And then font width.
You rotate the guide horizontally, place the pivot on the letter's left edge, and the letter's right edge must fall within the font width window.
And what about that strictest test, the stroke width, that absolute 15% requirement?
That's the final check. You align the line you're measuring with the narrowest window on the guide, the stroke width window. The line has to fit exactly within that window.
So if it's too thick, it fails.
Wow.
Too thin, it also fails.
It fails. The geometric guide uses light and shadow to give you a definitive visual pass or fail based on those programmed ratios. It eliminates all the guesswork.
It is truly stunning how this system translates such complicated math into a simple visual alignment. Before we wrap up, we should quickly look at 2 common tools where specialized knowledge is actually the key,
Yes.
starting with the 25-foot measuring tape.
This is one of my favorite details in the source material because it addresses a fundamental misunderstanding. Most people notice that the metal hook on their measuring tape is a bit loose, that it slides back and forth.
And they assume it's a defect. I've always thought that meant it was cheap and inaccurate.
It's the exact opposite. It is absolutely not a defect. It is a feature of high-precision engineering.
Oh, so?
The hook moves by precisely the thickness of the hook itself. So if you're measuring an external distance, the hook catches the edge and the measurement begins right at the 0 mark.
Okay.
But if you're measuring an internal space, you push the hook against the wall, and the gap created by that movement ensures the 0 point is still accurate. It compensates for the thickness of the metal hook every single time.
That is genuinely a shocking piece of knowledge. I will never look at a measuring tape the same way again.
It's built for perfect accuracy, whether you are pushing or pulling the measurement.
And what about measuring really small distances, like the clearance on a door sill?
Well, since the hook metal often obscures the actual 0 mark, the best technique is to start measuring from the 1-inch mark and then just subtract that inch from your final reading.
Simple enough.
And remember, for circumferences, like the diameter of a handrail, you have to force the tape to snap into a bend to break its inherent stiffness and allow it to coil tightly around the object.
Finally, the stopwatch. The tool reads to 1/100th of a second, which sounds ultra precise. But the expert notes say we should avoid recording fractional seconds entirely.
Right, because the precision of the tool is overridden by the inherent limitations of human reaction time.
Of course.
Studies show that human reaction time averages around half a second. So if you record a time of, say, 1.25 seconds, that final quarter second is almost certainly just measuring when your finger happened to hit the button, not the actual event.
So you have to stick to whole or half seconds.
To maintain the integrity of the audit record, yes.
So what we've really done today is take this stack of dense, often intimidating ADA standards and watch them be distilled into these simple, elegant, physical pass-fail tests.
That's it.
It really highlights the power of specialized design. It removes the barrier of having to be an engineering expert just to perform an accessibility assessment.
And the crucial takeaway is that the existence of these tools just reinforces the standard itself. Minimum accessibility requires 100% compliance.
Right.
So even if you aren't doing an official audit, understanding that your path or your ramp or your signage must meet these zero-tolerance physical standards. That's key to evaluating the true usability of any environment you're in.
And that leads us right back to that strategic challenge of the targeted audits. When resources are limited and incremental change is the only path forward, we have to ask a difficult question. Is it truly better to provide shallow, general improvements across many areas, giving a little bit of access to everyone? Or is it more impactful to focus deeply on one functional limitation group, like vision or mobility, to deliver full access and complete usability for that specific group sooner?
What's the real measure of success?
Exactly. What is the real measure of success when accessibility improvements have to be phased in? That's something to consider the next time you walk over a tiny, unnoticed vertical offset that could stop a wheelchair in its tracks.